Alrighty. You've done all the hard work up till this point, learning about sequences and series and convergence and really diving into the terminology of what this whole thing means. What are the components? What happens when you have your summation index together with X in there? Like all these things have built up to Taylor series and Taylor polynomials, which should be a big cool aha moment for you guys. All right, so let's talk about what this means. All right, so if you have a function, you can actually, if it's a continuous function over, let's say over the reals, you can actually break it down so that it looks like a polynomial. And for some of you, this is going to feel really good because probably deep down in your heart, you always wanted sine and cosine to be a polynomial and it never was. Well, today it gets to pretend. Okay, sine and cosine and every function that's continuous gets to be approximated by polynomials. Okay, we call them Taylor generically. That's the generic term, but if this A is 0, if this center, also known as A, if A equals 0, we can call it a Maclaurin series. Okay, so our Maclaurin polynomial. But even because it's so common to center these guys at 0, and Maclaurin takes more syllables than Taylor, we often say Taylor when we just mean Maclaurin anyway. So anyway, it's kind of a looseness there in our definition. But all of them are Taylor, and if we say Maclaurin, it means make sure the center is 0. Okay, now what does this mean? I'm going to let A equals 0 just to make everything look nicer. Let's look at a partial expansion here. What does this look like? So you're going to have a coefficient, and then you have a different coefficient times times x rather, and it could be, again, x minus 0. Another coefficient times x squared, another coefficient times x cubed, and so on and so forth. So you know that f of 0 has to be C0. Now we do this beautiful thing. We do term by term differentiating, which you wouldn't think it works, but it does, okay? And that tells you that the first derivative at 0 is C1. Now before you get too excited, watch what happens next. So for the first two, for f of 0 and f prime of 0, you don't have to worry about anything. You just like pull off these coefficients. But once you get to the second derivative, you have to start worrying about the nuts and bolts of what's going on here. You have to keep track that now these constants are going to start popping out at you. What do you think happens when you try to take the derivative yet again? And then at this point, you should start to see the pattern. Okay, at this point, you're going to get 3 times 2, which I'm going to rewrite as 3 factorial. And the x goes away, so f triple prime of 0 is 3 factorial c cubed. And generically, we have f to the n. So this is a script n. Sometimes people put it in parentheses to emphasize that this is telling how many derivatives. You're not raising to a power of. So sometimes it's in parentheses, sometimes it's just a script n so that you can tell that it's not a power. That nth derivative of 0 for Maclaurin is n factorial times that coefficient right there. Okay, now that's great, but that means what? It means that if you solve for Cn, you get this lovely formula. Keep in mind that for f of 0 and f prime of 0, we don't have to worry about n factorial only because 0 factorial is 1 and 1 factorial is 1. So that the pattern continues, but you just don't need to multiply things by 1. It's a waste of time. Okay, so once you get past that, then you have to be really cautious and don't forget that factorial piece. Otherwise, you'll mess up all your exercises. Okay, great. So now we have all these fun facts. Okay, so I guess I used I in one case and N in another case. I'm just going to clean that up a little bit. I'm just going to say I equals, so N equals 0, N equals 0, and then I'm going to just pull this piece over here and slide it up here. Hopefully that will make everybody happy. Okay, great. So now this is an easy two-way street, okay? This means, for example, we can do this easy stuff. Y is equal to, I'm just going to make something up. I'm going to expand this, and I hope you don't mind that I'm now putting the A equals something other than 0. That's fine, but you just have to make sure that they're all the same, right? You can't let this be a -3 and this be a +3, or you don't have a Taylor-Maclaurin type of situation. You just have a mess. But as long as you keep that thing centered somewhere, you can imagine as though you've shifted it back to the origin and you've just shifted it in the other direction for your own convenience. Okay, so now if you have something sitting there, you can say, aha, I know what y of 3 is. It's 7, and that's obvious because those terms will just cancel out if x equals 3, right? But now, you already knew that, but now you know y prime of 3 is sitting right here. You don't have to take the derivative. And you know y double prime of 3 is kind of sitting here, but you have to do what to it? You have to multiply it by 2 factorial. It's actually 8. Because think about it, if you were to take this derivative, what would you do? You'd multiply these guys together, right? That's what you would do first. So that still happens, right? And if it's a higher power, those exponents keep trickling down on you. Okay? So it's a really easy thing to do, and it makes a lot of exercises easier. So you can do an exercise like, let's say this. Let's say somebody asked you to find f of x so that there's a whole stack of derivatives specified at a specific point. Now, just again, keep in mind, you can't just like make that a 3 and that one a 7. You have to keep the center consistent. I'm not saying that that wouldn't be a solvable problem. It would just be a horrific nightmare to do those calculations. You could still solve for it. But because all your information is stacked at the point x equals 4, that makes this a very easy problem because we're using Taylor, and so this whole thing is super easy. So you just get ready. You're like, oh, this is an easy peasy question. All right, I'm going to say, you know, some kind of cubic. So I'm going to write, and it's centered at 4. So I'm going to just get ready to receive all my coefficients here, and then I'm just looking to receive some coefficients in front of these terms, right? And so I'm going to just go ahead and drop these guys in. The easiest ones are the ones down on the end where you don't have to worry about the n factorial. You just go ahead and put the 8, you know, f of 4 is 8, so you just dump it in. F prime of 4 is 7, you just dump it in. Now, we have to worry a tiny bit. We have to divide by 2 here because we're going the opposite direction than we were. So we have to divide by this n factorial here to put our coefficient in here, and then 1 over, in this case, 3 factorial, which is 6, and then the exercise is done, and all we had to do is divide by 2 and divide by 6, and there was really nothing else to it. Really easy problem. Okay, so you have some exercises that ask like this. They will say f of x equals, and they'll give you an f of x, and then they'll say find Taylor or Maclaurin, and it'll be 4n equals 6 or degree equals 6. That means you're not going to get an exact answer. The thing is going to go on forever, but you're only going to chop the first so many terms off, and then the rest of it goes on and you ignore it. Okay, so this is a very common thing. Let me show you a little bit about that. So Wolfram Alpha is a powerful tool. Please don't abuse it, but you have a really powerful tool at your disposal. You can just say, what's the third Taylor polynomial for e to the x? Okay, and it will just tell you. Okay, and we will explore this. But one of the great things it will do is it will actually plot this sequence of Taylor polynomials. So you can say, what's the first Taylor polynomial for e to the x? And it's just going to plot the 0th one, which is this horizontal line is the 0th Taylor polynomial, and then this is the first Taylor polynomial, is just the line, And then the second Taylor polynomial is the parabola. And you can watch these guys converge. And it becomes a little hard to see, I guess. There we go. You can just see that this guy is looking like a parabola, and it's trying very hard to hug that the e to the x curve. Okay, so this is a good exploratory tool for you. But for you to do these by hand, what it's going to mean is whatever n equals 6, you need 6 derivatives. Okay, so you're going to need 6 derivatives in order to do all this, and it means you'll end up with actually like 7 terms, because if it's a 6th degree polynomial, you get that constant in. So if you consider the constant to be a term, you get one more for free. That 0th piece. Okay, so let's do an example. Okay, and let's say the question asks us to use f of x equals sine of x and find the 6th degree Taylor expansion about x equals 0. And so how do we go ahead and do this? Well, the first thing we got to do is figure out what's going on with our derivatives. Derivative of sine is cosine. Next derivative is negative sine, and the next derivative is negative cosine, and then of course it repeats. But I like to do one more because I don't like 0. I'm just prejudiced against 0. I want it to go 1, 2, 3, 4, and then 5, 6, 7, 8. It just feels better to me. You don't have to do it that way. Okay, now f of 0 is 0. F prime of 0 is 1. F double prime of 0 is 0. F triple prime of 0 is negative 1. And then, of course, it repeats. Is going to be 0. So this part repeats. Okay? Now, if you're thinking in terms of, like, what am I going to do with this? So I'm going to re-sing this just to save space here. All right, so I want to construct this guy. F of x is equal to, and then we said f of 0 equals 0. So I'm just going to ignore that piece. There's no C0 term. C0 equals 0. So I'm going to ignore that. And then I have term 1, 2, 3, 4, and since I don't need this space, 5, 6. 6 more terms after that constant. Okay, so what are the coefficients going to look like? They're going to look like 1, 0, minus 1, 0, 1, 0. So I get to just get rid of all these even ones. There's no C2 term, and there's no C4 term. There's no C6 term, right? So actually just this, the fifth one is going to be 1. So this is term 5, term 3, and term 1 are the only ones we have to worry about. Now you may say, wait, I thought n equals 6. Well, that's true, but since we only need half of them, the other ones are kind of there. They're just invisible because they're 0. All right, so you're still going to get your 6th degree polynomial even though that last coefficient is 0, so you're good. So if you were asked for the 5th degree polynomial or the 6th degree polynomial, your answer would be identical. All right? Okay, now what else do you have to put in here? You have to put in here the x minus a. Luckily, a is 0, so it's just going to be x to the n. N is 1. X cubed, x to the 5th. That's good. Okay, I think I can remember the coefficients, so I'm going to erase this now. I also need n factorial. Oh, okay, so divide by 1 is not a problem, but I want to divide by 3 factorial, so it's going to be 6. And then I want to divide by 5 factorial, and I am not going to compute 5 factorial. I'm just going to write it as 5 factorial. At that point, I'm just going to go ahead and write this as 3 factorial so it looks good. And there's my answer, and maybe I want to make that, sort of squeeze that in a little bit to make it look nicer. All right, just so, don't forget this is a plus. It looks messy, but it was a plus, and then the next term would be minus x to the 7th over 7 factorial if you wish to continue, but the question didn't ask for that, but that's what would happen next. Okay, then I just want you to be aware that this can be rewritten, just assuming this just continues. This can be rewritten, and you can say, wait a minute, I'm only using the odd powers, so why don't I just do the following? Why don't I just say 2n plus 1 up here. And you're like, why would I do that? Well, it's because you're just trying to be conservative, and you're just compressing your notation. You're using this 2n plus 1 means you have a sequence of odds, and you still allow your index to go from 0 to infinity and march along like so. But you still have this problem. You have an alternating sign. So we haven't quite taken care of what we've written is not correct yet. It's a different function that's very famous, but not this one. So you can just put this -1 up here. Be careful that it's not n plus 1. Let's double check that this is working. When n is 0, we should get the first term. So try putting n equals 0. So this piece wipes out. It's 1. When n equals 0, you should test to make sure you get back to your first term, and double check that when n equals 1, you get to your second term, and when n equals 2, you get to your third term. Okay, so just double check that. That should all work out. Okay, you can do everything except possibly question 4 with all this information. I just want to give you a just-in-time hint for question 4. If you remember what we've been doing, it's actually a review, but I just want to make sure you're okay with that. So I want to give you a little hint on question 4. So recall that when you have a function that is increasing, f prime is positive when f is increasing, right? And remember that f prime is negative when f is decreasing. And also we have the concave up and concave down thing. All right, so concave up, so we have the second derivative is positive, or concave down, then the second derivative is negative. Okay, and that should be enough to get you through.